So, next we will be looking into the avoidance policy, deadlock avoidance policies. So, prevention is fine. So, prevention is actually trying to do something so that we know that this deadlock will not occur, but they are a bit synthetic solutions, we should say, because they are imposing different type of restrictions on the resource request type and all, and it is difficult for for writing a process by an application programmer, so that these resources are requested in that particular sequence. So, unless, so what will happen is that the programmers, they will ask for all the resources that they need at the very beginning, to just to avoid the possibility that okay, I may not be granted resources later. So, they will try to put all the resources at the beginning, so that they can play it safely and release only at the end. So, that actually affects the system resource utilization factor. So, not a very good solution always. So, next we will be looking into these avoidance policies. So, these deadlock avoidance policies, they ensure that the system will never enter into a deadlock state. So, somehow, so we have to guarantee this thing, by means of this resource allocation policies and all, that the system will never enter into a deadlock state. It requires that the system to have some additional a priori information available on possible resource requests. So, it assumes that for every process we know what are the maximum resource requirements of each types of resources for a process. So, so maybe I have got say 3 resource types R1, R2 and R3 in my system, and for process 1 maybe it so maximum requirement is say 3 instances of R1, 2 instances of R2, 5 instances of R3. Similarly, for P2 maybe it requires 1 instance of R2, it does not require any instance of 1 instance of R1, no instance of R2 and 4 instances of R3. So, these are all the maximum requirement for the processes. Somehow this has to be known, and naturally if the system follows this particular policy, then the programmer may be asked to provide at the very beginning what is the maximum resource requirement of different types of resources that is there in the system. So, simplest and the most useful model requires that each process declare the maximum number of resources of each type that it may need. So, for example, P1 requires at most 3 instances of R1 does not mean that P1 will require all of them simultaneously. So, it will require all the 3 together. It just tells that I may need at most 3 of R1, 2 of R2, 5 of R5, R3, and during execution, so it will put the individual requests, but the total request will never be exceeding 3 for R1, 2 for R2 and 5 for R3 simultaneously. So, this the process has to declare the maximum number of resources of each type that it may need, and the deadlock avoidance algorithm, it will dynamically check whether the resource allocation state, it will dynamically examine the resource allocation state to ensure that there can never be a circular wait condition. So, it will check whether there can be a circular wait or not, and so the resource allocation state is defined by the number of available and allocated resources and the maximum demand for each process. So, this resource allocation state, so what is the currently available and allocated resources, that list, and the maximum requirement for the processes. So, that will define this resource allocation state. So, based on this, we can formulate some deadlock avoidance policy. We will define some state to be a safe state and some other state to be unsafe state. So, this is a diagram. So, that tells if this is the total state space that we have. So, some of the states are safe state and some of the states are deadlock state. So, safe states are such that if a system is in safe state, it can never go to deadlock directly. So, if so this is the total set of states. Now, it says that so if this is a state here and this is a deadlock state, then we will never have a transition from this to this. So, this is never there, but there are some states which are unsafe in nature. So, there may be transition from safe state to unsafe state, and from the unsafe state there is a possibility that it will make a transition to a deadlock state, Of course, it is very much possible for that from an unsafe state it again comes back to safe state. But what we will do, we will not allow this type of transitions at all, because if the system goes into an unsafe state, then there is a possibility that it may go into a deadlock state, with knowing fully well that in actuality the system may not be making this transition, but it will make a transition coming back to a safe state. But just to ensure that we will never go to a deadlock state, we will stop this type of transition which will take the system from some safe state to some unsafe state. So, we will elaborate on this slowly. So, if we just go back, define what is a safe state. A system is in safe state if there exists a sequence P1, P2, Pn of all the processes in the systems, such that for each Pi the resources that Pi can still request can be satisfied by currently available resources plus resources held by all the Pj where j less than I. So, let us try to understand what does it mean. So, at any point of time I have got a number of processes in the system P1, P2 up to Pn, and I have got the resources. Suppose I have got say 3 types of resources R1, R2 and R3. Now, this P1 to Pn they have got some requirement for R1, R2, R3. So, they are having some so P1 is holding some amount of R1, it for its completion it may need some more of R1. So, that is depicted by the maximum requirement that has been declared by the process P1 at the beginning. So, process P1 for its completion which how many more instances of R1, R2, R3 are required, that is known. Similarly, for process P2 what are the extra R1, R2, R3 instances needed, so that is known. Now, if you can somehow ensure that with the currently available free instances of R1, R2, R3 and so with the currently available free instances of R1, R2, R3, so if you can satisfy the requirement of P1, then I can say that P1 will complete. After that, this currently available resources plus the resources held by P1 they will be released. With that, if I am able to satisfy P2, and so the P2 will finish off and the process continues. So, I just then I take all the resources which are free after P2 has finished, then with that if I am able to finish off the next process. So, among these processes P1 to Pn, so if you can find a sequence in which all these processes requests can be satisfied, okay, by this requirement, that is so when I am talking about say Pi, so Pj, so for completion of Pj the resources which are free plus the resources held by for the process Pi, for the process Pi, so I can say that for process Pi I have got the resources which are currently available plus the resources which are held by the processes before Pi in this chain. So, I have got this P1, P2, Pi, say Pi minus 1, Pi, Pi plus 1, etc. Now, when I come to this process Pi, then all the resources which are available at this point plus all the resources held by these processes. So, they are all free now. So, with that if we can satisfy Pi, then I can say that Pi can be completed. So, the system will be safe state if I can complete all these processes. So, P1 to Pn. So, if I can complete all the processes in this way, then the system is not in a deadlock state. So, this cannot lead to a deadlock state. So, this is a safe state. So, this actually what it means is that if Pi resource needs are not immediately available, then Pi can wait until all processes Pj j less than I have finished executing, and when they have finished their executing, so they will release all their resources and then Pi can get all these resources, they then execute and return the allocated resources and terminate. And when Pi terminates, now Pi plus 1 can get the needed resources and so on. So, this way it can continue. So, if we can find a sequence of processes by which all the requirements of the processes can be satisfied, then we say that the system is in a safe state. So, with that we can look into this diagram once more, when the system is in safe state. So, if the system is in any of these state in this subset, then all the requests for all the processes can be satisfied always. But if the system is in unsafe state, then all the requests cannot be satisfied. Though may be the case that the system the processes they make requests for their maximum resources, as a result the system goes into deadlock state. But at the same time we must understand that a process may not request further resources, but rather release a few resources. Maybe it may so happen that a process P1 it requires say 3 of R1 and 2 of R2. And when I am looking into the system code, the process code at some point of time, maybe I am at this point. So, it has at this point it has got 1 of R1 and 1 of R2 with it. So, it can ask for 2 more R1s and 1 more R2 before releasing this resource, and that may lead to deadlock, but we must understand that maybe in between. So, it releases these resources also. So, it releases some more resource. So, it releases say 1 R1 and after some time it releases 1 R2, then it requests for 2 R1, then it requests for 1 R2. So, it may happen like this. So, you see that so when it releases the resource, maybe from this unsafe state it can come back to safe state, that can happen. But there is a possibility that without releasing resource the process will request for further resource, as a result the system may go into a deadlock state. So, we will try to avoid this we will try to avoid putting the system in unsafe state, so that there is a potential to go to the deadlock state. So, this is what we will be trying out in our this deadlock avoidance policies. Now, deadlock avoidance, it will ensure that the system will never enter into an unsafe state. Single instance of a resource type. So, use a variant of this resource allocation graph, and based on that we can formulate and some avoidance policy. If there are multiple instances of resources, then we can follow something called a banker's algorithm, and this banker's algorithm. So, this will be ensuring that this deadlock can be avoided. We will not go into this will not go into the unsafe states. So, resource allocation graph based policy. So, this is applicable only when we have got single instance of every resource. So, multiple instances are not there, every resource there is only a single instance. Then the same thing, that each process must a priori claim maximum resource use. So, every process must tell which resources it needs, since there is only a single instance. So, telling about how many is of no issue here. So, basically we tell what are the resources that are needed by this process, and use a variant of the resource allocation graph with something called a claim age. So, claim age, so this is Pi to Rj, it indicates that the process Pj, so process Pi may request for resource Rj. So, this is not Pj, so this is Pi. So, process Pi may request for Rj and represent by a dashed line. So, what I was telling is that maybe process P1 its maximum, so it requires the resources R1, R2 and R3. So, that is declared by the process at the beginning. At present maybe process P1 has got the resource R1 allocated to it. So, process P1 has the potential to ask for the resources R2 and R3. As a result, so we will put the claim ages to these resources R2 and R3. So, we will put a claim age for R2 and we will put a claim age for R3. So, this is what is told here. So, if we will put a claim age from Pi to Rj, indicating that the process Pi may request for Rj and it is represented by a dashed line. Claim age converts to request age when a process requests a resource. So, after some time P1 may actually request for R2. So, when it requests for R2, then this age will become a solid age. Okay. So, as long as it is a potential claim. So, this is a dashed age, but when the process request actually makes a request for the resource, then it will be modified by a solid age. and request age will be converted to an assignment age when the resource is allocated to the process. So, after some, if the system allocates the resource to the process, then this age will be converted into an allocation age by removing. So, by this age will be converted into an allocation stage by putting the arrow on this side. So, these resources are now allocated to process P1. So, when a resource is requested, when a resource is released by the process, then the assignment age reconverts into a claim age. So, after some time process P1 might have released this resource R2, but since till the lifetime of P1 ends, so it can again ask for the resource R2. So, in that case, so we will be converting this assignment age into again a claim age. So, this is how this whole thing will work. So, when a resource is released by a process, the assignment age is converted into a claim age, and resources must be claimed a priori in the system. So, this they must be required at the beginning. A cycle in the graph implies that the system is in unsafe state. So, if you construct a graph like this having this claim age, resource request age and grant age, allocation age, then the situation that we get from the graph. So, that is if there is a cycle in this graph, then it is in unsafe state. So, this is what we will try to make. So, this is like this. So, resource allocation graph with claim ages. So, P1 is holding, so there are two resources R1 and R2 in the system. So, P1 can ask for both R1 and R2. So, we have got two processes in the system P1 and P2. So, P1 can request for the resources R1 and R2, and P2 also can request for the resources R1 and R2. Now, P1 is holding resource R1. So, we have got an allocation age from R1 to P1, and it has a claim on R2. So, since P1 has the potential to ask for R2, so there is a claim age from P1 to R2. Now, P2 is requesting for R1 and it has got a claim on R2. So, it is at present P2 is requesting for R1 and it has got a claim for R2. So, this is the situation. Now, there is no cycle in this graph. So, naturally this system is safe. So, why the system is safe? You can understand that even if say P2 in this situation. So, if this P1 is given R2. So, if P1 and P2 both of them come up with their requests. So, I can give this R2 to P1. So, P1 will finish off, and then this R1 and R2 can be given to P2, and P2 will also finish off. So, non-existence of cycle in this particular resource allocation graph with claim ages. So, that means the system is in safe state. So, it cannot go to a deadlock state. Now, going further, so consider the case where claim age from P2 to R2 is changing to an assignment stage. Suppose we do it like this, that P2 has requested for this R2, P2 has requested for this R2 and it has been granted to it. So, so R2 was free. So, when this age was not there, so if we look into the previous slide, then R1 is given to P1 and R2 is free. Now, suppose P2 requests for R2. So, this claim age converted into a request age and the system allocates this resource R2 to P2. Then what happens? The situation becomes something like this. This R2 is allocated to P2. So, P2 holds a request for R1 and there is a claim that P1 will request for R2. Now, the situation is that there is a cycle in this graph. Now, you see that I cannot give R1 to P2. So, P2 cannot proceed. So, this R1 is currently with P1. So, P1 without releasing R1 may request for R2 because there is a claim age here. So, this claim age at any point of time may get converted into a request age. So, as a result P1 may request for R2 and there will be a cycle coming into this graph so there will be a cycle coming into this graph. So, so that is existing here and if this claim is converted to a request, then there will be a deadlock. So, this is an unsafe state. So, this is not a deadlock state at present, because till now P1 has not requested for R2. So, this is a potential request. So, if P1 does not request for R2 at any point of time, if P1 before P1 instead of P1 requesting for R2, if P1 releases R1, then of course, the system will go back to the safe state, because now P2 can be given both R1 and R2, P2 will finish off, then P1 comes up some other time, it requests for R2, then it is getting R2. So, that is possible, but this is an unsafe state. Okay. So, it can go to a deadlock state or it can come back to a safe state. So, both are possible. Now, there is no deadlock at this point, but it is an unsafe state. So, we can proceed with this. So, resource allocation graph based algorithm is like this. Suppose that process Pi request for a resource Rj, the request can be granted only if converting the request age to an assignment age does not result in the formation of a cycle in the resource allocation graph. Otherwise, the process must wait. So, whenever a process is requesting for a resource, so if you convert the request age to an assignment age and see that there is a deadlock, there is a cycle in the resource allocation graph, then there is a potential for deadlock. So, we have to be careful. So, we have it is going to an unsafe state. So, we have to stop that allocation, though resource is available. So, it will not be allocated, just to avoid that case that it may go to a deadlock state. The next algorithm that we will look into is known as Banker's algorithm. So, this Banker's algorithm, so there are multiple instances of a resource type. So, if there are multiple instances, then that cycle detection algorithm does not work. So, we have to go for some more complex algorithm, and one such algorithm is the Banker's algorithm. So, each process must a priori claim maximum usage, that is fixed, as I said that a process must tell how many instances of different resource types that it may needs in its entire lifetime. So, that way each process must a priori claim the maximum usage. When a process requests a resource, it may have to wait, and when a process gets all its resources, it must return them in a finite amount of time. So, a process requests for resource, it may have to wait because the resource may not be granted, and when the process gets all its resources, then it should not be that it holds the resources infinitely. So, it will use those resources and release all those resources. So, that should be done. So, process execution time is finite. So, this is like an interest free bank situation where a customer establishes a line of credit and borrows money in chunks that together never exceed the total line of credit. So, it asks for money that does not exceed the maximum limit that it has. Once it reaches the maximum, the customer must pay back in a finite amount of time. Once it has reached the maximum value, then the amount must be, the entire amount must be returned within a finite amount of time. So, that is why this algorithm is known as Banker's algorithm. So, if you look into the similarity between these statements here, so each process must claim a priori the maximum usage. So, this is similar to a customer establishing a line of credit. So, what is the maximum credit that the customer may ask for? So, that is there, and then borrows money in chunk. So, this is basically the requesting for the resource. So, this is when a process request a resource, then it has to wait. So, that way it has to wait for that. So, here also the customer is asking in chunks. So, that is requesting for the resource and may have to wait, because if the bank finds that it may violate the total amount of money that the bank will have with it to satisfy all the customers. So, that may not be that may be violated. So, and maybe only if some other customer pays back the whole amount, then only this customer will be given the money. So, like that, and when the process gets all its resources, it must finish within finite time and release the resource. So, that is basically the third condition, that when the amount reaches the maximum, then the customer must pay back in finite amount of time. So, that is why this algorithm is known as Banker's algorithm, because it mimics the behavior of a banking system. Now, the data structures that are used in Banker's algorithm are like this. We have got n number of processes and m number of resource types. So, we have got an array available. So, it is a vector of length m. If available j equal to k, then there are k instances of resource type r j available. Then we have got a max n by m. So, max I j equal to k, that means the process P I request at most k instances of resource type r j. So, this is basically the process I requesting for resource r j what is the maximum number of instances that it can ask for. Allocation is again an n by m matrix, and allocation I j is equal to k, then P I is currently allocated k instances of resource j. So, if allocation I j equal to k, then P I, so that it is currently allocated of k instances of resource j, and need is another array n by m. So, need I j equal to k means P I may need at most k more instances of r j to complete its task. So, need I j is basically a derived matrix. So, this is max I j minus allocation I j. So, the maximum requirement for individual processes have been mentioned in the max array, and allocation is the current allocation for the processes. So, if you subtract this allocation from max, so that gives the need. Okay. So, need is basically a what is the extra amount of resources that the processes may ask for without releasing any further resource. So, that is the need array. Now, the safety algorithm, so it actually checks whether some allocation will be whether the system is in safe state or unsafe state. So, it works with two temporary arrays, so work and finish. So, work and finish, they are vectors of length m and n. Initially work is equal to available and finish I is false for all the processes. So, if there are n processes, the finish array has got n entries in it, it is a Boolean array and it is all initialized to false. And the work array, so this is an array of resources available for particular type. So, this is work is available, work is initialized to the currently available resources. Now, what the algorithm does is that it tries to find an I such that finish I is false, that is the process is not yet finished, and the need of the process I is less than the work. So, whatever is available. So, work is the currently available one. So, need I, the need of the process I is less than the what is available in the working array work. Then we can satisfy that particular process to completion. So, if no such I exists, that means there are two situations. One possibility is that finish I is true for all the process for all I. So, in that case all the processes have could be completed with the available resources. So, the system is in a safe state. Other possibility is that we could not find any process for which the second condition is satisfied, that is need I less or equal work. So, that condition could be satisfied. So, as a result, so that is also a situation when there is a the system becomes unsafe actually. So, if none of them are true, then we could find an I such that the process has not yet been finished and its need is less than the currently available one, currently available resources. So, in that case we update the work array, because we assume that this whatever this process needs, so that can be given from the work array. So, accordingly this process will be able to finish off, and once the process finishes off, all the resources that are currently allocated to process I becomes free. So, as a result my working array is enhanced by having all those resources claimed back from the process. So, this work array is enhanced by this work equal to work plus allocation I, and finish I is set to true. So, because this process is assumed to be finished, and then it goes to step 2, it tries to find out another another process which can be finished now with this augmented work array. So, this way if we can find that all the processes can be finished with the currently available currently available set of resources in a particular sequence, then we say that the entire system is in a safe state. Otherwise, the system is in unsafe state and we have to avoid coming to an unsafe state. So, we can utilize this safety algorithm to see like how this allocation decisions can be made whenever a process makes a request for a resource. So, it is first the safety algorithm will be run to see whether it can lead to a potentially unsafe state, and if we see that it is not leading to an unsafe state, the system will remain safe even after this allocation is done, then only we will do that allocation, the resource allocation will be done only at that time. Otherwise, the process has to wait for the resource to be free. So, we will continue with this in the next class, discussing on the allocation algorithm.